Hello, this is the Ice Thickness Detection Study Group. I am Wyatt Patterson.
I'm Steve Kanopko.
I'm David D'Arcangelo.
All right, to get started with the background of our study, each year there are several accidents caused by unsafe ice conditions with winter outdoor activities. So whether this be ice fishing, snowmobiling, skating, hiking, regardless of the activity, everyone's heard the stories of people falling through, and a lot of that is due to people being unaware of changing conditions and like the lack of knowledge out there on what is safe conditions between different online sources. It can be confusing on what is technically safe ice for thickness level, clarity, whether there's presence of a current. So a lot of this results in people having to rely on their own judgment for determining what is safe and unsafe. And a lot of that is through their sensory inputs, so their sight, their feel, their auditory response. So our goal is to see how successfully people can determine the thickness of ice with auditory and tactile signals from Spud Bar, which is a tool used mainly in ice fishing for detecting ice thickness. And the goal of this is to provide new safety information on the topic. So to get into our test plan, the design of this test was to conduct a subject survey of the ice thickness. So we had a body of about 20 samples of Clarkson students come and test ice thickness via the Spud Bar. For the test plan, ice sheets were frozen ahead of time and then were suspended on plywood stilts in the container shown in the picture and were suspended above a body of water in the bin. What this did was allow us to model as closely as we could to a frozen lake with the water beneath for um, similar acoustic responses. Um, but while preparing this, an ice bath was made for the water, and the sheets themselves were kept as at close to the freezing point as possible to prevent thermal shock, and that would crack the ice if that happened. Then we gave a quick debriefing to the subjects before they tested to make sure they understood the goals of the project and what they were supposed to do, make sure they were safe. And then we let the subjects each tap the ice, holding the Spud Bar 3 inches above and tapping it 3 times. And then they were given an estimate. Actual thickness of the ice sheet was then recorded for comparison and for error analysis. And then another independent variable in this was our snow cover, which we deliberately changed through the trials to see how the thickness of the snow cover on the ice affected the results. Other parameters measured were past experience of the subject, maximum acceleration of the Spud Bar, which was recorded using the Firefox app, and whether the test subject thought the ice would be safe to walk on.
All right, we have a very simple 10-step procedure. The first step is to create our ice baths. We then read our instructions to subjects and make sure everyone's safe and knowledgeable about what we're going on and what we're doing. We then choose an ice sheet sample ranging from 1 to 6 inches. We then choose the most suitable frame for the sheet so that it fits nicely in our bins. We then place our frame into the bin, fill the water for the ice bath. We then attach straps to the ice sheet before putting it in the tub. This just allows for a quicker process to take the sheets in and out and an all around easier process. We then present the subject with the first sheet. They will tap the sheet lightly with the Spud Bar and we'll record if they have any previous experience, we'll record how thick they think it is, and we'll record if they would walk on the ice. We then remove the sheet without them looking. We then replace with a new sheet and add a light layer of snow to obscure their vision a little bit. And so they'll have to rely heavily on their auditory and vibrational response from the Spud Bar. We then we set this up in the same way as we established in steps 3 to 6. Once the second trial is done, we change out for an additional sheet and we cover it with a heavier layer of snow for even greater obscuring of their vision. And then we repeat this between all of our test subjects. So we have a fairly simple equipment list. Some things we had to pay for, some things we didn't. We had two freezers that we used in Camp 172, and we had three bins that we purchased. We got water from the sink. We made 5 wooden frames. We have 4 clamps, our spud bar. We use a mobile phone for the Firefox app that we use as an accelerometer. We have 2 straps. We use crushed ice that we acquired from the Science Center, and we have a phone holder. So we had to pay for the bins, the plywood, for the frames, the clamps, the straps, and the phone holder for a grand total of $172. Our safety was considered to be very low risk for this. There were only a couple actual risks. These included handling the cold ice and a slightly sharp spud bar. Our risk could pretty much be entirely mitigated by using gloves to shield us from the cold ice and properly instructing all of our subjects on how to handle the spud bar for our experiment.
All right, so next we're going to go into some of the results that we accumulated throughout our test and made with the data that we collected. So first, we made a QQ plot, and this was basically just to show that the data that we collected followed a normal distribution, which can be seen through the linear path that the circles here follow. And the reason that this graph kind of looks like a step function almost is that normal distributions are dependent on continuous random variables, and with this, we didn't really instruct our subjects to guess on hard counts. So basically, they were guessing 1 inch or 2 inch, and not like or basically just integers and nothing like 1.3 or 1.5. And this kind of caused this step function to kind of exist. So next, we made a histogram, and this was basically made to show that the data collected throughout our experiment followed this normal distribution, which you can see in the graph that kind of follows that bell-shaped curve. The histogram also provided a way for people to guess where the data would fall. Along with this, it can be seen that the mean of the data sat around 1 to 2 inches, with which take it as you will, but we thought that this was a pretty interesting epidemic that occurred with our data. And to further this analysis, we made a 95% confidence interval, which shows us that we can be 95% confident that the ice or where the ice estimation will fall. Because both ends of our range end in an overestimate, we can conclude that most of the time people will overestimate the thickness of the ice. And this can be concurrent and shown in real life applications where a 1 to 2 inch overestimate could cause someone to have a breakthrough and be injured. So lastly, we also performed a multivariable linear regression, which was performed to model error as a function of the parameters collected throughout the test. Although this test is statistically significant, seen on the right side table with a significance value less than 0.05, the model had an R-squared value of 0.443, which means that the model is relatively poor. This can be shown by looking at the parameters individually, as 3 of the 4 parameters on the left side have their own p-values that are greater than 0.5. And the fact that we weren't successfully able to model error shows that this application is a problem in real life, is a problem in the real world. This was also seen by receiving some verbal confirmation from different subjects that they had no idea what the ice thickness was.
All right, to conclude, we found that for most people, when determining ice thickness with auditory and tactile response, there's an overestimation of around 1 inch. This particularly becomes a problem in real world application and like early and late winter, as like a thinner sheet of ice that you're standing on, a 1 inch difference could be quite significant, could result in accidents, as is seen out there in the real world. When it comes to the limits of our model, we made quite a few assumptions when making our setup based on the real world system. A lot of this was done for ease of the experiment, as it is a laboratory experiment. We were not going to be able to either freeze or handle large sheets of ice safely and effectively. So some things to investigate for future work would be like the size of the ice sheet, how that affects the results, your stand and container material, how their vibrations affect the acoustic response, and the depth of the water beneath the ice. Again, how that affects the acoustic response. We had several subjects note that it sounds quite different than a frozen lake, which again should just be explored for future results to make this data applicable. For future work, we also thought that it would be good for people or for future work to focus on if people can detect changes in ice thickness, because in the real world scenario, a person will most likely have an auger with them or would be willing to check the ice thickness before they participate in outdoor recreation. So drill a hole, measure it, make sure that it's safe. But from there, because of changing conditions, that's where a lot of issues arise. So it'd be interesting to see if people knew ice thickness and associated that with a certain acoustic response, they could then detect changes in ice thickness from there. And we kind of saw that with our data. People were able to verbally say whether ice was thicker or thinner as they were testing, and would make for a more interesting experiment. Finally, our last remarks would be to be conservative when making decisions regarding the safety of ice and outdoor recreation. No afternoon skate or hike or afternoon fish that you're going to catch is going to be worth your life. And we just want to make sure people out there are being safe. I can't figure out how to stop the recorder.